welcome to the fourth part of our unit on oscillatory motion and waves. In this portion, we're actually going to introduce the concept of a wave. So what is a wave? It is propagating periodic motion. Propagating, what does that mean? It means it moves through space. It's not just tied to one location. Okay. So what direction is it going? Well, if we have a wave, and it's easier to draw transverse waves, and I'll introduce what exactly a transverse wave is versus a longitudinal wave a little later in this portion. If we have a transverse wave, we have the medium doing this, and the transverse wave would be moving that way. And this speed is the wave speed, which is not the same as what we were doing in the last unit with the maximum speed during simple harmonic motion. Okay, this is the wave speed. Okay. So some definitions. Amplitude is the maximum displacement again from equilibrium. Wavelength. Wavelength is one we haven't seen before, but wavelength is very similar to period in that wavelength is the distance that the wave travels in one cycle. Okay. The letter used for wavelength is the Greek letter lambda, which looks kind of like a T tipped on its side, and the units of wavelength are meters. I should also say the units of amplitude are also meters. It's a displacement. Period is exactly what we had before. It is the time for one cycle. So the time needed to complete one full oscillation. Again, capital T measured in seconds. And frequency is the number of cycles per a given time. F and units of hertz. So now that we have these definitions, we can define the wave speed. So the speed of a wave is going to be the characteristic distance of the wave divided by the characteristic time for the wave. This is not traditionally how this formula is written, though. Instead, we use that the period is 1 over the frequency. So 1 over the period would equal the frequency, and we say that the wave speed equals the wavelength multiplied by the wave's frequency. Okay. And this equation, V equals lambda F, holds for every single type of wave. Maybe it's a sound wave or an electromagnetic wave. It doesn't matter. It holds for every single type of wave. Now, as I alluded to earlier, there are two general types of waves. We have longitudinal waves where the oscillation is parallel to propagation, and a transverse wave where oscillation is perpendicular to propagation. The one I drew a minute ago was a transverse wave, so let me show you what that looks like first. So here is a transverse wave. You can see the wave itself is moving to the right, but the oscillation of the particles, so you can see the one on the y-axis here, is perpendicular to that. Okay. Notice while the wave is always moving, every little bit of this wave motion is moving to the right at the same speed, the particle here stops at the top and the bottom and is undergoing a simple harmonic motion. Okay. Which is a good point. The particles that make up the medium that a wave travels through do not propagate with the wave. And I have a simulation in just a second for longitudinal waves, which illustrates that fairly nicely. let's go look at longitudinal waves. For longitudinal waves, I'm going to go to the other one first. What you have is a oscillation back and forth that's in the same direction as the propagation, which is again to the right. Here you can see little lines showing the oscillatory motion of the particles making up the medium here. If we go to the other simulation, here we're putting a longitudinal wave through a spring, and you can see that the coils of the spring move around, and you can see how they compress and stretch apart. But the coils don't actually travel with the wave. If I watch this orange one, for example, that orange one always stays in the vicinity of this spot where my cursor is. This concludes this portion of this unit. In the next part, we're going to begin the discussion of superposition.